Cindy Douglin, and start off with the PDF D1. You can see I have number 10, and starting with 10A, that's basically saying that you're going to show that the surface temperature of the Barnard star is about 3,000 Kelvin. So, using the Wien law, I start off by, I show that the surface temperature is about 3,000 Kelvin. That's what I'm trying to find. So, you use this equation right here, and you can find that on page 423 in the textbook. And then to find the temperature of the star, you do 2.9 times 10 to the negative 3 over this, and you plug in the 940 nm and that was what the peak wavelength is. And you times that by 10 to the negative 9, and you get 3,085 Kelvin. So yes, it's proven correct that the star's surface temp is about 3,000 Kelvin. Now we can tell that the Barnard star is, if you look at number part 2 of 10A, it says just why Barnard star is not likely to be a white dwarf or a red giant. And the Barnard star's temperature is too low to be a white dwarf, not luminous enough to be a red giant. And the charts on page 425 in the book compares like the color for the temperature in Kelvin of the star, the correlation, and then the luminosity for the star type, and that's how I was able to determine that actually it's a red dwarf star. So yeah. Now moving on to 10B, and moving on to 10B, it's looking at the determine in astronomical units the distance between Earth and Barnard's star. It was about 6 light years away, based on like the color and the luminosity of the star. It's a red dwarf star, and there's charts in the chapters to look at. Part 2 of 10B, the parsec is 3.26 light years. And when you double that, you get the 6 light years for the part A, or 0.543 arc seconds per pixels. Yeah. And then for number 3, that was to calculate the parallax angle for the Barnard star as observed from Earth. And then part 3 was to outline the parallax angle is measured, how to find it, and you measured the position of the star with respect to the fixed background then within 6 months between readings, the parallax angle is half the total angle. So yeah. Now my next question is number 20. And it's like you have to draw a circle around the stars that are red giants, and then you have to label the circle R. So I have to do stuff on the paper. Yeah. So putting it up real close, I labeled 2 of these outer skirts as R for the red giant stars, and what makes them red giant stars is that the temperature has to be between 2,000 and 3,500 Kelvin, and the luminosity has to be 10 to the third, because the luminosity is a level 3. So I looked for any, well, technically, sorry. Now, the white dwarfs have to be Well, they're at the bottom right here, these two. And what makes them white in the first place is that, excuse me, it's 7,500 to 10,000 Kelvin. And that's, am I reading this right? Yeah, and the luminosity, because it says, this is for part B, it says to circle white dwarfs. The luminosity has to be a dwarf, it's about, so it'll be like negative, what's the thing called? That's why it was like under -1. And yeah. And then the third one was draw a line through the stars that are main sequence stars, which is all here. It's kind of like the line of best fit. Also, if you look on page 426 in your textbook, in the HR diagram, it really did help with this question. Now moving on to 20B, it says, explain without doing any calculations how astronauts can deduce the star B has a larger diameter than star A. I made a mistake on 20A, part 1. Actually, it's these two. It's not B. B is not a red giant. For part 3, the part 3 for 20A, star B has a lower temperature, and star B has a slightly larger luminosity, but it's quite similar of star B compared to star A, and therefore, and also star B has a larger surface area. Therefore, star B has a larger diameter than star A.